Given a measurement with an estimated uncertainty of 17.1 grams plus or minus 0.1 grams, what is the percent error represented by this uncertainty? So there's actually a new thing here that's being introduced for us. So maybe, I don't know, maybe I'm a bad professor because I didn't put that on the key concepts page. Isn't it bad if I ask a question about something and I never gave any of you or any of us the definition of that? Well, I did it. Happens sometimes in life, I guess. But so that's the new concept, percent error. What could that possibly mean? Well, maybe we can think about that a little bit here, because what is error really about? We've said here this is a measurement with an estimated uncertainty. And it turns out when I say error and uncertainty are pretty much the same thing. The word error comes from mathematics and has kind of this really kind of rigorous definition in kind of advanced statistics. It's kind of, my recollection is that it refers to there's various examples of them, but they refer to different measures of variance for different kinds of situations. But the error in this case really is that estimated uncertainty. So estimated uncertainty is more common type of language that you see in a physics class. In that sense, that language really comes from the discipline of physics. The language of error comes from the discipline of mathematics. But either way, if I say the error is 0.1 grams, and that's really 0.1 potential error there, right? Measure of variance, really, estimated uncertainty, but out of a measurement value of 17.1 grams, right? So if we looked at like, well, as a ratio, how big that is, right? That might make sense to do, because like if this was plus or minus 0.1 grams, and if it was, instead of 17.1 grams, let's say it was like 1700 or 17 million or whatever grams, maybe we would want to measure in kilograms then, I suppose. But that would be different, right? Because if that number is smaller, the relative effect perhaps of this error here, or potential error, or amount of variation, expected error is another way we could describe that, but estimated uncertainty is what physicists tend to say. It's going to have a magnified effect when this number is smaller, right? So one way of looking at that is, we're actually going to call this the relative error in lab, is to look at the ratio of that error to the measured quantity. So just make that as a fraction, 0.1 over 17.1. If you wanted to, you could put like grams upstairs and grams downstairs, but those would just cancel out. So it really is a pure number when we say something is a relative error. And then I can go to my calculator and write down what this is. I usually, if you wonder about sig figs on this, I mean, I've kind of said for some parts of this class, for a lot of parts of this class, I'm not too picky about sig figs. There's a whole other story with that, with errors, that's going to come up in lab a lot. My usual rule of thumb for like a relative error, and that's going to maybe apply to a percent error, is 3 is usually good, maybe 2 at the least, because otherwise sometimes you get round off issues, excuse me. Maybe error is the wrong word, since this kind of is related to an error anyways. The language can get a little confusing, but I'm getting that number, so I'm just going to go 3 sig figs here, 0.00585. But if you think about this, like from a very basic math class point of view, and somebody said, here's a decimal, give me a percent, right? Wouldn't this correspond to just 0.585%? And guess what? This was the relative error. Well, the percent error is basically the relative error expressed as a percentage, which now when you look at that, hopefully we can all agree that wasn't that huge a stretch. I think it was because I ran out of space on the key concepts page. There was already so much there, so I figured I would just tell people when we get here. So let's check our answer here and see, there it is. Those numbers match, so I think we had the right idea, that means.